we will focus on the sedimentary deposits on Mars also because this is a peculiarity of Mars. So today, first we will introduce some theoretical aspects. I will start them, Beatrice will continue on the spectral data, and then we will move on with the practical activity. So why the outline of what we are going to speak about today is a general outline of the sedimentary rocks and environments on Mars, their geographical and stratigraphical distribution. We will have a brief digression on the categorization of geoscientific maps, because we can map sedimentary deposit, but we can map everything in different ways. So we will have a brief look at that, and then we will look at the problems and peculiarities of, in general, planetary geological mapping, and also of Mars sedimentary deposits mapping. Then we will focus on stratigraphy, which is specifically important for the sedimentary deposits, not only, but specifically for sedimentary deposits. And then we will have a look at few of the sedimentary systems which have been proposed to have been on Mars. First of all, why sedimentary rocks are important in planetary geoscience. Actually, not only in planetary, okay, on Earth is a planet as well. So I suppose planetary geoscience is correct. They reflect surface processes which occur on a planetary body. So in this way, they provide tools to understand which processes shape them, in which the positional environments they were deposited, in which climatic conditions, and also the evolution through time of the environments, as well as the climatic conditions, which gives us a clue on how the global conditions of that place and in perspective of all that planet change through time. This has implication, of course, in the evolution of climate. This is obvious, but also in the evolution of life. So I know that not all of you are geologists, so I hope I'm not too much pedantic with these slides, but just to introduce the kind of sedimentary environments that we can encounter. We have clastic sedimentary environments where the material comes from a source area where they are subjected to weathering and erosion. Then they are transported through gravity, ice, wind, or water, and deposited somewhere along this path. Then these sediments will be subjected to diagenesis and will become from sediments to sedimentary rocks. These are called alloctonous deposits because they come from a source area and then they are deposited somewhere along this path. Then we have chemical depositional environments. Chemical deposition environments where deposition occurs through precipitation in a closed basin at the surface or in the immediate subsurface. These deposits can be also, of course, these are autochthonous deposits because they originate directly from the very same basin, and they can be or not associated, that can have relations with clastic depositional environments. In this example, we have clastic deposition environments nearby, just beside these autochthonous deposits. Going to Mars, the geographical distribution of sedimentary deposits is extremely widespread. This is not even a very new image, but still very good coverage of sedimentary deposits, which have been detected through high-resolution imagery. In white, we have high-rise data. In black, mock data. Still, a lot of sedimentary deposits covering most of Martian surface. If we go through time, so if you look at the stratigraphic distribution of this deposit, we see that we have a change through time. We have through the Noachian and the Spurian period of Mars geological history, which corresponds to the, we reach up to somewhere in the Archean. If we compare this to terrestrial geological times, we have sedimentary environments which reflect relatively rich water condition, outflow channel, valley networks, or sulfate precipitation, or in any case deposition. In more recent time, we have still sedimentary deposit, but different. We have the polar layer deposit, which probably were active throughout all or in different intervals of Martian geological history. We have glacial deposition, and it's not in this sketch, but Aeolian deposition has been active throughout all Martian history. So there are, but maybe I can show this better here. This is a sedimentary mineralogical evolution, which have been possible using spectral data. Again, the stratigraphic scale here. Until the mid-Noachian, clay-bearing deposits have been detected through using spectral data. So this suggests water-rich conditions. Then from the late Noachian to the Hesperian, these clay-bearing deposits are associated to intermittent sulfate-bearing deposition, which suggests an increasingly water-limited content. Then during the Hesperian, the water content drops dramatically. There are some events which suggest the presence of water, but the conditions are supposed to be to become hyperarid. Okay, I was very superficial here because Beatrice Baschetti will later go in more detail in this topic. So just a brief introduction. But I want here to open a very brief digression, because this is true not only in planetary geology, it's true always in geology, but it's specifically more important in planetary geology. Never trust individual evidences which are not included in a geological context. So the expression I just showed, sedimentary mineralogical evolution, makes sense only if included in a broader geological context. I didn't tell you that the clay-bearing deposits are associated also to morphologies which are suggestive of water-rich conditions. This is important also in the scientific interpretation, which comes after the mapping job, so to say. Going to mapping, mapping sedimentary deposits is important because this is the only tool to assess the geographical distribution of a given unit, but especially because it's the only tool to assess the vertical and lateral relations between the different units. So it's the prerequisite to build a story, a geological history, sorry. My brain is not enough to control this tool. So mapping the sedimentary deposits, actually this is true not only for sedimentary deposits, prerequisite to associate laterally coeval landforms or units, which means that we can reconstruct a landscape, not just single features, but entire landscape, which means environments and their evolution through time. Then we will be able to understand controls on the environmental and climatic change, and finally, hopefully, to infer the implications on the habitability potential. Still, mapping Mars has problems and peculiarities. This is actually true not only for Mars, but all the when we are dealing with remote sensing analysis, because on the planets, of course, because mapping is the scale of mapping are instrument independent. Of course, even on Earth, you have geological maps at different scales. This is normal, but this is something we choose because we go in the field, we map, we see everything, and we decide which is the best scale to express what we saw. On the planet, or specifically on Mars, we cannot do that because we have to rely on the data that we have. Then this is a remote sensing method with no or very limited ground truth, because we have very few rovers on the ground. We have limited information on rock composition, but at the same time, we have relatively limited weathering, so we have a good preservation of morphologies. This combination of facts led to the traditional approach in planetary mapping, which has always been either chronostratigraphic or morphological rather than strictly geological. I will go back to this in a while. And also, these problems lead to problems in this fact lead to problems of scales and equifinality that I'm going to introduce in a while. Problem of scale as instrument dependent. This is an example. If we start from our left here, we see this is the same place on Mars. At HRSC scale, we can observe a fan-shaped feature, maybe some light tone terrain here, but we can have a morphological approach. At CTX scale here, we can better describe the morphologies because we have different, we can discriminate different, more fan-shaped features, but we can also discriminate two different units, this light tone terrains here and the darker tone one. If we move to high-rise resolution, we can actually see that the light tone terrains are bedded, and we can observe the contact, the stratigraphic contact between the two units. So when we go and map, we need all the data sets that we have available in that specific area, because we need to understand everything. So specifically describe the units, describe the boundaries, and of course, this is the base for the following scientific interpretation, because map are the prerequisite for scientific interpretation, but at the same time, the map should be consistent throughout all its extension. We cannot have part of the map extremely detailed, the other part which are more rough. So we need to decide the scale of our work in order to fulfill the science goal and keep the same detail of the representation in all part of my study area. We will see this better in the practical part. Now, a few words on the possible cartographic approaches. We can have feature-based mapping, we can have process-based maps, which can be interpretative, so geomorphological or morphostratigraphical maps, or between brackets, objective or relatively objective, so geological maps. Then we can have chronostratigraphic maps and landing site maps devoted to landing site characterization of resource exploitation. Today we will focus just on the first for landing site characterization as the difference that needs to address also engineeristical constraint, because you need to focus also on landing, on the landing safety and trafficability safety after the landing, while resource maps deals a lot with spectral data in order to detect for example, specific minerals. But we want to focus today on the first four mapping approach. Feature-based mapping represent the cartography or just one or few specific landforms or structure or mineral or whatever, in order to address the distribution of such elements over generally the planetary body or a very large portion. This is an example. This is the Mars Global Digital Dune Database. So it's a very good tool. I know where all the dune fields are on Mars. This is a very good tool for a preliminary analysis of a specific scientific problem, distribution, geographical distribution. When we go to the process-based maps, we can be interpretative, so geomorphological maps, or more objective. Interpretative, why? Because geomorphological maps are based on the representation, which can be qualitative, quantitative, where possible, representation of landforms and their specific genetic interpretation. So they are topical maps oriented to science investigation. I map and I interpret, for example, this is an example, Tiras Valles. This is a not super recent map, but very well done and very, very clear. We have deltaic deposits here, alluvial fan deposits here. We have channel, fluvial channels. So this is clearly interpreted as a lacustrine, fluvial lacustrine system. Of course, in this case, when we will go to prepare our map and we will design our attribute table, the attribute table will depend on the interpretation of the single landforms and structure. As I told you before, this has always been very, very used in planetary settings because, especially on Mars, because landforms are nicely preserved. Still, sometimes we need a more objective approach. Step backward. Geological maps are on Earth the first and basic geological knowledge of a specific territory. So we go in a place, X sunt leones, we know nothing. First of all, what we want to know are the lithological characteristics and their change through vertical and lateral changes. Because this is the most objective. One rock is one rock. Still, this on the planets very often is not possible because, again, as I told you before, we have very few rovers on the ground, we have very few information of the lithological composition. So somebody could argue that it's not really possible to speak of, strictly speaking, geological map in the planets, not only on Mars. Still, we have the need sometimes of a more objective cartographic product. This is something that can be needed when you are not sure about interpretation, for example, or when you want to build the geological framework in an area which is very complex, when you don't have yet ideas of the processes and environments of formation. So I will go back to this point in a while. Just I want to finish what I was telling about the cartographic approach, telling just a few words about the chronostratigraphic maps, because chronostratigraphic mapping is very used in planetary settings because it is a very useful tool to link geological units to their stratigraphic ages. So we don't care about their origin, genetic origin, but we want to reconstruct their relative or absolute age of deposition, timing of rock formation, of rock modification of a specific surface. The stratigraphies on the planetary bodies are generally based on crater chronology. And this is the most famous map for Mars. This is a small piece of the global geological map of Mars by Tanaka et al. 2014. Now, let's go back to our problem of scale in order to try to understand the problems of geological mapping, of planetary geological mapping, and how to address this problem. Problem of scale. Okay, we already saw that we have multiple data sets and that our job is constrained by this the available data set. But there is one more problem comparing to the Earth. Here we have, if we work, when we go and work in geology, we always need to address problems using different scale of analysis. So first of all, we have the geological context. Here we have Earth. This is an example from Ethiopia, the Lole, and this is Mars. The geological context has comparable scales, 10 to 100 kilometer scale, more or less is the same. But if we move to the observation measurements, so we move to detailed observation, on Earth, for example, we have this mound, which is about 1 meter, which is, okay, not so different from these mounds, which are on Mars. We have this polygonal pattern, 1 meter scale, more or less, which are more or less similar on Earth and on Mars here. But on Earth, we can go, on Mars here, we stop. We cannot see more. On Earth, already in the field, already without taking samples in the laboratory, we can go down to millimeter scale of analysis. So this is something that change the kind of observation that we can do on Earth and on Mars. Then there is another problem, that is the problem of equifinality, which can be defined as the fact that similar effects may be generated by different combinations of causative processes. So, for example, this is a landform on Mars, the mounds we saw earlier. They could have been originated as erosional remnants, so they could be not even depositional feature, but erosional feature, or they could be pingos, so formed in glacial settings, or mud volcanoes, such as this one, for example, or, sorry, it's blocked, or spring mounds, such as this other example. I'm not even mentioning the volcanoclastic possibility. So this is very complicated. And how can we cope with this problem, with these two issues, so to say? The only way is to integrate all the available data and define of a geological context. So we have to switch from the interpretation of the single landforms, for example, the mounds I was showing you earlier, in order to interpret associated landforms, what on Earth we would call a landscape. So the interpretation is much more constrained. In order to do this, we need to understand the unit lateral and vertical distribution. Again, this is why we need to do geological map, and we need also to well define the stratigraphic relations, which is actually part of the geological map perform. Geological map is not just to color unit in a different way, it means also to understand their mutual geometric, which implies stratigraphic relations. Then we will be able to perform interpretation with the classical methods of geology, the multiple working hypothesis approach, and the analog studies. This has been introduced fantastically by Becker in 2014 for planetary settings, but it's what geologists do each day, anywhere. So we formulate different genetic hypotheses, we follow the consequences of this genetic hypothesis and test this hypothesis and the hypothesis that arises from the consequences of the original many hypotheses. I was mentioning stratigraphy. Stratigraphy is of course always important in any kind of maps. Is specifically important for the mapping of sedimentary deposits. The principles of stratigraphy are the one very known by Sten already in 1669, original horizontality of the beds, superposition, lateral continuity, and cross-cutting relations. This is something very well known. These are the base to reconstruct the relative dating of the geological units. Then we can express, I will go back to this issue on Friday when we'll speak of the stratigraphic relation, but still, we can express the stratigraphic relations in using space diagrams, such as this one, for example. So we will reconstruct the geometries as we see them from the geological mapping, or we can, in this case, of course, for example, this channel, we see this channel, of course, we do not, we cannot express the fact that here we have erosion. So these deposits are not coeval with this deposit, which are older, because this channel eroded material which was deposited earlier. It's a bit of a mess, no? This kind of reconstruction respect to the time. So we can also use a space-time diagram where we include the meaning of each unit respect to time. So we put all the units in order respect to their formation, but also we include the time that is not represented. For example, here we have an erosion, so some time was deleted from our record. We will have not this time anymore because it was eroded. This is included in this reconstruction. So we have some missing time. So we will know which kind of deposits are present in our area, which kind of time is represented in our area, and when the units are laterally coeval or where they are superposed in time. The missing time can be sketched in different way, can be represented in different way. We have non-conformity when we have deposition of non-sedimentary rocks and sedimentary rocks on top. In the middle, a surface in correspondence of which we had erosion and non-deposition, which means that we miss time here. Here is the same, but we have inclined sedimentary rocks, which were inclined, erosion, non-deposition, and deposition of other sedimentary rocks. In this case, we have sedimentary rocks, bedded sedimentary rocks, which have more or less the same attitude, but in the middle, we have a surface which helps us to say that there was no deposition and erosion, so some missing time. So two parts of a different geological history of that specific area. This is an example of an unconformity from Mars. Here, this image was taken by Curiosity, and this is an unconformity. So between the deposition of this rock, there is some missing time, erosion and non-deposition, and then this unit arrived. I hope I am try to be more clear using this example from Eberswalde. Eberswalde is a very famous place on Mars because this delta-like feature, so to say, was considered the smoking gun evidence when it was discovered in 2003 by Malin and Edgett. It was considered to be the proof of the presence of persistent water stable in the surface of Mars. But some olivine have been detected in that very same place. And olivine is considered a mineral which is immediately alterated by water. So how is it possible this? If you go in more detail, we see that actually this landform consists of two different units. Even more detail, we have a light tone bedded unit here and a darker tone unit on the top. If we look more clearly, we see that there is the contact between the two units is not continuous, but it's a disconformity, because the topmost unit is not in contact with the very same bed below. There is erosion between this bedded unit and this darker, more recent unit. Moreover, if we go and look at the A2 abundance, we see that water is abundant in these light tone terrains. So basically, olivine is widespread in this darker tone coverage, which post-date the deltaic deposition. What does it mean? It means that the deltaic history or water-related history of this part of Mars is related to this part of the succession, the bedded light tone part of the succession. Instead, this darker tone part of the succession corresponds to another part of Eberswalde crater geological history. So there are two different stories, and we have to pay attention not to mix them. Otherwise, our scientific interpretation will be completely wrong. So again, olivine-rich deposits site above the disconformity, two different geological history. Now, I'm going to open another digression, which is maybe a little bit pedantic. I was speaking we are always speaking about beds on Mars or layers, but we have to remember that our resolution allow us to see not the complete detail of these beds. So maybe the word bed set would be better. Bed set means a number of superposed similar beds. So maybe we can, when we see this, for example, this light tone beds, maybe this is not one, these are maybe 10 similar or 15 or whatever similar beds, and we cannot recognize them because our resolution do not allow this. So probably bed set would be a more precise word to express this. Now, everybody use beds and it's totally okay. So it's not, I don't want to focus on a problem which is just a terminological problem, but we have to be conscious when we compare different beds in different areas to use the very same data set, because otherwise this would not be just a terminological problem, but would become a substantial problem because we would compare different things. So, like for example, they did properly in this paper. They compared beds using the same data sets, namely high-rise data set. So, just to pay attention to do this always. Now, sedimentary units have lateral terminations, so beds terminate somewhere. This is important because it allows us to reconstruct what was going on in that basin. We have truncation, so beds can be eroded in some way. We can have on lap, this fascion here with horizontal bed. We can have beds which are truncated at the top dramatically, like here, this is a top lap. We can have this geometry, sigmoidal geometry, this is called off lap, while the down lap is this geometry where inclined beds, puff, go and reach a subhorizontal surface. More in detail, this is an erosion, we have beds here which are eroded, and we have the deposition of a younger deposit. This is a disconformity, this is an erosional truncation. Very important to recognize this because it means that some time is missing here. On lap, horizontal beds, hitting against an inclined surface. Why this is important? Because on lap means that we are infilling the basin. This geometry forms when the basin is infilled. on lab. This is another example. We have these beds here, which are more or less horizontal, and they, here you see nicely puff against the, in this specific case, is the inner side of the crater, so on lap, and this is the graphic representation. These beds are draping the surface and onlapping against the surface itself. Of left downlap, without telling you the definition, just to show them, which is probably more clear. This is an example from Mars, taken again by curiosity. You see these beds, tuck, tuck. They go and hit this subhorizontal surface. It means that sediments is transported far into the basin in this way, moving from here onward. This is a downlap. Then we have lateral transitions. So we have units which pass laterally to other units, which means that these deposits are coeval. In geology, we say that they are conform to Walter's law, but to I hope, express more clearly, we have layers here in correspondence of these mounds. We have layers outside of the mounds, and we see that they are continuing puff. These layers are continuing from the mounds to outside of the mounds. It means that these units were formed in the same time. They are coeval. Now, let's go back and pick up again what we were mentioning at the beginning, geomorphological and geological maps. Here we have a geomorphological map, so we have landforms, genetic interpretation, so we have a delta with delta plane, delta front, pro-delta deposits. Genetic interpretation. Geological maps, I told you already, we have no geological information, so, okay, lithological information, sorry, with the exception of the few derived by the mineralogical hints, but we do not know the rock, we know something about the mineralogy, so we do not have the lithology of the units, so we need to define the units on the basis of relatively objective means. So the characteristics of the deposits, color, texture, they are layer, no layer, maybe sedimentary structure at all scales. And we have to define the morphologies. So the geometries without the interpretation of the environments at all scales. So morphology in terms of geometry. So no, I'm not saying what form, what shape that morphology is, but just the geometry. And of course, the thickness, whether they are geometries, erosional or depositional, or whatever. And of course, the stratigraphic position within the succession. This is an example of a geological map of the very same place. We have a substratum, non-sedimentary rocks. We have a layered succession with, this is again Eberswalde, also the layered unit which corresponds to the so to say deltaic part of history of the crater, and we have the post-deltaic coverage divided by, we have a non-conformity between the substratum and the layer deposits, and the disconformity between the layer deposits and the darker tone unit of the, we call it mantling deposits. You can go even more detail, realizing, but because here we have a very high resolution, nice coverage, so in this case, it's possible also to show this facies map even in more detail, distinguishing between a breccia unit, a polygonal pattern unit, and the smooth unit. But okay, this is just a particular. The aim is that why I want to do geological map in order to distinguish the observation from the interpretation. It's not that I'm not interpreting, but I want to keep the interpretation separated in order to, if I will understand in the future, or someone else will understand that this interpretation was wrong, still my observation will be useful and good. In order to do this, we need also to have an emphasis on stratigraphic boundaries. That's why we need 3 different layers with different information in the same cartographic product. So we will have contacts in order to focus on the stratigraphic relations. The contact can be continuous, can be unconformable. We will have a layer on the geology in order to focus on the description. So as you saw before, just description, and another one with the geomorphology in order to focus on the genetic interpretation. In order to define the unit with all these characteristics, we need a place to perform our observation. On Earth, we have the stratotype. It's called the stratotype. On the planet, we better call it reference area, but it's the same thing. It's a type section. It's a place, physical place, which serves us as a standard of reference for definition of a specific unit. So we go in a physical place where all the characteristics of a given unit can be observed before starting to map. So we will go in the place which we can observe at best this unit at all scale in order to, so to say, make our eye and discuss and have all the elements to map this unit elsewhere. Example, again, Eberswalde, we start HRSC scales. We can see, we want to observe the light tone deposits I was mentioning you even before. At HRSC scale, we can just see that they are light tone associated with a fan-like landform. At CTX scale, we understand that it's rugged, that it's layered. It unlaps here the very rugged unit. At high-rise scale, we can see that it's rugged because it is disrupted in polygonal pattern and it's unconformably covered by the dark tone unit. Of course, the ground truth would be the best way to tie our observation in a more detailed way in order to understand all the possible also sedimentological aspects of the specific area. This is a very, I would say, already historical important image, even if it's just 2005, because it's an image taken by Opportunity, which represent these aeolian dune fields with some playa deposits intercalated. Now I will go very quickly, because it's very late, to have a look at some of the sedimentary systems which are present on Mars. This is a very inexhaustive example. We have on Mars, we can have fluvial lacustrine deposition environments, outflow channel, light on deposits, ice-related aeolian deposition. We will focus on the first 3. First of all, sedimentary basin. What is a sedimentary basin? It's a low area in the crust in which sediments can accumulate. On Earth, this normally occur in the process forming sedimentary basins are not entirely, but almost entirely linked to plate tectonic. On Mars, again, it's not the only process, but the most important is impact cratering. To form a sedimentary deposit, we start with sedimentary process. Sedimentary process, in this case, it's an aeolian, or we see clasts which are transported by wind in different way. With time, they form a landform, in this case, a dune. Landforms are short-term features on Earth, long-term features on Mars, so which means that they go down into the deep geological time. with more time, we have the formation of deposits. So stacking landforms originate this deposit, which are long-term features both on Earth and on Mars. In order to see them, we need erosion and exhumation. This is difficult on Mars because we do not have plate tectonics. Ideally, when we do a map of the landforms, we do a geomorphological map. When we map the deposit, we do a geological map. Ideally, this is the difference. Fluvial casting deposition environments, again, very roughly, we have alluvial fans, valley networks and channels, deltas, and lacustrine systems. Alluvial fans are the relatively steep cones that form as a most proximal alluvial deposition at the break over the slope, usually when a bedrock river debouches in a plain. Now, bedrock rivers are the one running in the mountains or in the inner ring of the crater, and they do not deposit, they just erode. So they do not contribute to the stratigraphic record because they do not leave sediments. Alluvial rivers here are the ones that contribute to the deposition because they deposit material which remain in the stratigraphic record. This is an example of alluvial fan on Earth, a very classic one, and this is an alluvial fan on Mars in Holden crater. We can have alluvial fans, okay, when we reach the break of the slope, which if we have more alluvial fans which are juxtaposed, we have a bajada. If the bedrock river reach the break of the slope in correspondence of a standing body of water, which can be a lake or a sea, we have a fan delta. Instead, if we do not have a break of the slope, but simply a loss of competence because water is lost because of evaporation, of infiltration, of course, this is classical of arid climate, we have a terminal fan. Valley network, this is a distribution of all the valley network on Mars. So these are actually the two proposed possible shorelines which might confirm or suggest the presence of an ocean in the northern plane of Mars. But still, this is the distribution. Actually, this is a nice example of future-based mapping. And this is an example of valley networks. We have sapping channels also that are formed by the erosion of groundwater with this. This is an example from Earth, from Utah, with this amphitheater head, very classical. Groundwater and contribution from surface water. This is an example from Nirgal valleys on Mars, very classic example of sapping channels. In the alluvial plain, we have channels, but also overbank deposits, which are made of the levee of the channels, the crevasse when the flood debouched the crater, or floodplain when transimates the flood transimates from the channel. The main point is that these deposits are made of mostly fine-grained material. These fine-grained material are much easier to be eroded with respect to the coarser grain material which are here in the channel. This means that through time, this is the beginning, no? We have the channel material, coarser, this is finer grainer. With time, after the channel goes, the flood goes away, erosion starts, wind starts to erode the material. It will be able to erode this floodplain material. It will not be able to erode the channel material. This will lead to exhumation. Exhumation is a process which happens on Earth. This is again Utah. And on Mars, this is a very nice example from Aeolis dorsa of an exhumed channel. This is why on Mars we have so many exhumed channel. Then we can have stacking channels. Again, I was mentioning you that it is very difficult to see this on Mars because we do not have plate tectonics which expose this succession. In this case, Salese et al. Were lucky because they found, well, were lucky and also brave. They found this, if you look at these surfaces, these are channels stacking one on top of the other. So these are deposits of channels. This is Earth, so exactly the same style, the same fashion. It means that here water was persistent with a long time, for a long time. Then we have delta, when a bedrock or alluvial river enters a standing body of water. So fan delta if it's a bedrock river, delta if it's an alluvial river, which consists of a delta plane, delta front, where you start to have interaction with the standing body of water, and then pro delta in the basin. Okay, this is again Eberswalde, the most classic deltaic example. These are examples from Sabrina Vallis, Tiras Vallis, Sabrina Vallis, many deltaic deposits. This is another nice example. This is Sabrina Vallis. And of course, now it's going to be very, very popular, Jezero crater, because Perseverance just landed there. This is an image from above. This is a reconstruction of the geometry with these inclined layers making this offset geometry, a downlap here where the red cross, red arrow is, downlap, it means that the sediments are delivered within the basin. And this is one of the first images taken by Perseverance. So we will know better in a while about the internal geometry of this body. Lacustrine systems are quite difficult to be detected in the sense that coastal systems in lakes are poorly developed even on Earth. Moreover, coastal deposits are easily eroded. That's also why it's so difficult to prove the existence of an ocean on Mars. They are not so distinctive geomorphological elements, just flat basins and some terraces, flat basin floors, sorry. And this is an example of in situ taken by Curiosity within Gale crater of, you see, these flat deposits, finer grained deposits. Very quickly about the catastrophic flows, because this is an example where actually planetary processes, planetary morphologies help to understand better Earth processes. Catastrophic flows were known at the beginning in the Channel Scablands, very famous place where some rivers were blocked by the advance of glacier sheets during the Pleistocene, and later so forming these huge lakes that when ice start to retreat, were debouching a lot of water, catastrophically releasing water to form these Channel Scablands. These events led to the erosion not only of the quaternary loess deposit, but also of basaltic rocks, leading to the formation of for example, this is an example of a clast. I mean, that's why it's called catastrophic process. This is a giant current ripples, and this is a valley incision with two valley incision. These are huge processes which were longly not understood even on Earth. On Mars, we have these huge channels, sometimes associated with chaotic terrains. They have sign of multiple processes of erosion, especially there are erosional features. This is an example. These are all outflow channel, huge very huge features. This is an example from Ares Vallis, and this is how it looks like. We have this flat valley with these huge grooves. In section, they appear like this. You see the scale are 10 kilometers. This is, I mean, really giant features, which give you plastically the idea of a catastrophic process. They are often associated to chaotic terrains. So not always, but often. So this is, sorry if I'm going very quickly, but I want to finish. Just to mention also very quickly the light tone deposits, because these are quite interesting in the sense that we have these thick layered materials that can reach up to several kilometers, spread in different geographic and physiographic distribution, but they are characterized by the association to hydrated minerals, especially sulfates, which makes them very interesting. They are present in valles marineris, in the chaotic terrains, or as a crater in fields. In valles marineris, they are super thick, kilometers thick. They appear to drape the morphologies, the previously existing morphologies. They appear to dip outwards. There's, you see here, for example, this is a paper where they show they were measuring, the dip of the layers, and they show that they appear to dip outside of these features. Then we have these deposits associated to chaotic terrains. They postdate the chaotic terrains. You see this nice on-lap pop against this knob, or this knob pop. So they postdate, the formation of the chaotic terrains. Then they can be in the cratering field, such as, for example, in this crater, this is Firth crater. They are bedded, you see here. They are associated with mounds, not always, but sometimes. And okay, this is a geological map, but we will focus on the geological map and geological section reconstructions later on. So I am going to skip this part because I guess it was already quite too many things I was mentioning. So very quickly, just to wrap up, sedimentary deposits are the key to understand environmental and climatic changes. You need to map them as a prerequisite to make science on them, so to say. So first of all, you have to decide the type of mapping and the scale of mapping according to what are your science aim. So this is something that you have to carefully think before starting your work. Try to be consistent throughout the whole map, because the map should have not parts which are more detailed than other. The description of the units should precede the actual mapping. So first define the unit, describe the unit, then start to map. And you will not put too much emphasis on stratigraphy. Stratigraphy is very important to define the relative ages between the different units in order to understand the evolution of the sedimentary process and environment through time. Just to go back, not to mix the information and mix together two parts of different geological histories. You want also to understand which time is not preserved in the geological record. This is also very important. And to evaluate lateral relations, to interpret not a single landform, but an association of coeval landforms. Thank you for your attention. Thank you especially to Angelo Rossi, who gave me a lot of material. I'm totally indebted. The GMAP and also the teacher of the Master in Planetary Science, they gave me a lot of material, and I'm sorry not to put your single name, but thank you very much, and sorry, probably I was too long.